Hi everyone, we project visual reality lab simulation. We have a three member and Dirk, Andrea, and Mirza. We have two advisor, Dr. Chong and Dr. Moreno. Problem statement. This project is a visual reality simulation for an in-person electrical engineer lab could be used in the future remote learning experience. The simulation will replicate a current lab that we perform in the person using a 3D visual space, a visual reality headset and sensor. Did it improve remote learning for in response to the COVID-19 pandemic, which forced lab to be administered online? The online platform for the current lab are limited hands-on experience that are necessary for the student learning, research, and job opportunity. Project deliverable. Simulation output accurate data from students to you in order to complete the labs. Sensor function at the field by to show the student argument during the lab. Starting with the simulation to track progress to the quiz that are embedded in the simulation, properly embedding code to the system such that the headset, goggle, and software communicate. Purchasing goggle that we now run the 3D visual environment software and accurate software. Writing code for the simulation that react to the data given by sensor and device sizing requirement. Product should not exceed 1.5 pound. It means student can wear very comfortable. Design approach. Our project uses software to simulate the activity of the environment in real environment lab room. The software will use Unity like the last form from the simulation run on the goggle, Oculus Quest VR goggle to show visual environment and runway sensor. Mu sensor give us the data and runway route. Okay, system diagram. Simulation structure, student input go to the computer receiver, and simulation give the student data respond to the active, and final one is the output computer display simulation data. The learning feedback diagram, the student input and controller simulation content, the output improves student learning. In this format is runway sensor feedback where student engage.
This is a flowchart of the simulation procedures where we'll be mimicking the diode experiment from the Lab 2 course. Using the controllers, the user will begin by building the circuit from the outline procedures. The function generator will have a predefined input value for the experiment, and the user must connect it properly as the input to the circuit. The user will then connect the probes of the oscilloscope and be able to view the output waveforms. To move on to the next part of the lab, the user will be tested with questions pertaining to the pre-lab and the results of the experiment, as well the feedback that is provided with the continuous readings of the biosensors. For the design of our systems, we have two main hardware components. The first is the Oculus Quest VR headset, which has the goggles the user can use to move and look around the simulation, and the hand controllers, which users can use to interact and manipulate items in the simulation. The second hardware component is the Muse 2 sensor that has a total of 7 EEG sensors to measure the brain activity and is also able to output compatible Excel CSV files. For the software aspect of the system, the simulation was coded on the Unity platform in C# and has 4 different subsystems, which are the environment, the user interface, the lab equipment, and the testing and feedback section. For further analysis of the brainwave activity, we look into the absolute power values that are obtained through the sensors using a third-party application, the Mind Monitor app. The absolute power values are divided into frequency bands. For our system, we looked into the alpha band and the gamma band. The alpha band has 7.5 to 13 Hz bandwidth, and the gamma band has a bandwidth of 30 to 44 Hz. Signals in the alpha band correlate with relaxation, so the higher the peak values of the signal, the less information the student is processing. while the gamma band displays signals correlated with concentration. So the higher the peak values, the more the student is focused on the task. For the hardware development, we used a pre-built non-invasive sensor such that it is able to be worn with the Oculus Quest goggles comfortably and can output CSV files in real time. As well, the Oculus goggle can be easily interfaced with the simulation from the computer. In this hardware demo, we begin by testing the Muse2 sensors on participants to analyze the output data to see the comparison of brainwave activity for a user that is unstimulated versus when they are stimulated. We are able to see the live feedback from the sensors in the forms of raw EEG and absolute power waveforms. The data points are then sent from the app to a computer as a CSV file for further analysis. Here we see a user wearing both the Muse2 sensor and the VR goggle headset. The two devices pair well together as the VR goggle is able to securely hold the sensors against the forehead for better skin contact to allow for more accurate readings from the EEG sensors. With the VR goggles, the user is viewing the VR lab simulation that is being mirrored from the laptop screen. The user is able to manipulate the components of the simulation with the controllers of the VR goggle headset. The Muse sensor is continuously recording the user's brainwave activity. The final Excel CSV file is sent to the computer where the simulation takes it as an input for an analysis of student engagement. The file has a particular cell that contains the final score, which is calculated from the raw EEG data obtained from the sensors. This cell is then fed into the simulation for the feedback section and recommends further instructions.
The first step of the software development portion is building the environment. The environment was built with all the elements embedded into it within the Unity software. This includes physics, cameras, audio, and lighting. The second part of software is the user interface. The user interface is complete with all objects in the simulation. This includes menus, the flow through the simulation, on-click events, and the logs that show what the user is doing when they click a certain object. Finally, we have the main portion of the coding, which is the lab equipment. We want the lab equipment to respond according to what it would in an in-person lab. All materials were fabricated, the resistors, diodes, breadboard, etc., to have corresponding code to match their behavior in a real-life circuit. The oscilloscope and function generator outputs could be toggled using the oscilloscope mode of the simulation, which has embedded code in it to have the same response as an in-person oscilloscope and function generator. Here are a couple code examples for the lab equipment. There's a lot more than this, and you can dive deeper into the code within the lab report posted on our website. We begin our software demo with a look at the walk-around mode of the simulation. This is an optional mode, as through testing we learned that this mode was not the most user-friendly, as everyone who tested it developed motion sensitivity. Therefore, the normal mode of the simulation was created to reduce the amount of motion a user must perform to limit sensitivity. Here we see the main menu, procedure, and circuit building portions of the simulation. The procedure follows the diode lab procedure for the USF Electrical Engineering Lab 2. The circuit building section includes square meshes that are coded to interact with the tips of the electrical components. Users can select different resistor values based on lab procedures, rotate and lengthen components, as well as place oscilloscope probes for the desired circuit output. One key difference between an in-person circuit build and one done in the simulation is that the simulation is pre-wired with the function generator inputs into the ground and source rows defined on the breadboard, just like if one were to attach function generator outputs to those rows in an in-person lab. In the oscilloscope view, users can select what channels are visible, auto-scale or manually scale, as well as pause the simulation and put their cursors to read out values on the graph. Furthermore, the oscilloscope output can be saved directly to a computer in Excel CSV format using the Save buttons. You can see here the measurement was taken on April 25th at 7:04 p.m. and the file outputted matches the exact same time. Finally, we see that there is a testing and feedback section, which will be shown in a moment. The testing and feedback section gives instructors and students an idea of student engagement and performance through traditional quiz sections and through Mind Monitor performance sections. And here's our work division. Andrea did most of the coding portions. Mirza did more of the brainwave analysis and Muse sensor portions, and Duke did more of the documentation portions. However, all of the team worked alongside each other whenever needed. Thank you.